Greetings. Welcome to week 2 of Advanced Object-Oriented Programming. As we did last time, we kind of went over and started looking at terms first. And I'm going to take that same, way to do things as far as getting an understanding of the key terms. Then we're going to come back and talk about those terms in more detail. So what we're going to do is we're just going to go through some terms here that we have, and then we'll continue on from there. So in week 2, we're talking about collections, performance, and performance. And so these are some simple definitions of some of the key terms you're going to have in this particular week. Java Collections Framework, a built-in library in Java that provides ready-made data structures like lists, sets, and maps. These are basically programs that have already been created for you, and they're ready for your use in the form of interfaces. Behavior, how a data structure acts, how it stores, orders, and retrieves data. Performance, how fast the data structure performs operations like adding, searching, removing items. Design trade-off, a choice between the benefits and the costs. Example, is it faster lookup or is it more memory usage? Scale, how will a system perform as the amount of data grows? Correctness, producing accurate and expected results. Efficiency, using time and memory wisely when solving a problem. Some of the core collection types, which we'll be going into more detail, are lists, an order collection that allows duplicates. Example, if we haven't really used an array list. Set, a collection that does not allow duplicates. An example, if we have a hash set where we're hashing to a given position. Map, stores key value pairs. Each key must be unique. Example is a hash map. Queue, a collection designed for processing elements in order, usually FIFO, first in, first out, or LIFO, last in, last out. We'll talk about that later too. Will be cases where we'll be using that, both FIFO and LIFO. DQ, a double-ended queue. Elements can be added and removed from both ends. Some collection characteristics, ordering, whether elements are stored in a specific sequence, like insertion, orders, sorted order. Duplication rules, whether a collection allows duplicate elements. Lookup performance, how quickly the collection can find an item. Memory characteristics, how much memory the structure uses and how it manages storage internally. Hash-based collections, collections that use hashing for fast lookups. For example, hash map and hash set are both examples of hash-based collections. Okay, falling into the object contracts and a hashing section, we have equals. Method used to determine if two objects are logically equal. Hash code, method that returns a number representing the object for hashing purposes. And contracts, rules that must be followed. For example, if two objects are equal using the equals execution, they must return the same hash code. Under performance reasoning, we have big O reasoning. We'll be getting into some detail on that as far as whether a particular operation is O1, ON, or O log n. O1 being constant time. ON means linear time, which means that as the data requirements get bigger, then the cost of doing that grows with that growth. And log n, which is basically saying that we're for the amount of activity that we need to do, if something's O log n, we cut the processing in half. Okay, so we'll be talking about those in more detail here shortly. Transversing collections, we're going to be talking about iterators, objects used to loop through a collection of one element at a time. And list iterators, a special type of iterator for lists that can move forward and backwards when I'm going through the given list of items. Okay, so if we're looking at those items, those are the items that basically are going to cover the key points of what we're going to be doing in week 2. Yeah. So with that, as always, what I'm asking you to do is, do I need to memorize these? Yes, I want you to memorize because I want you to know exactly what they do. And whenever we do need, you see this again, you'll say, I know what it's doing. Okay, so with that, let's jump into the regular video lecture that we're going to be going through. We're going to see these again when I start talking about the in-class lecture for those of you who will be in class versus those who are online. But here's some of the key terms that we want to get across that we're kind of putting out there for week 2. Okay, opening. Welcome. Okay. Last week we discussed abstractions and professional API design. This week we're going to do one of the most important architectural decisions in software engineering. Okay, we want to choose the right collection. We talked about the Java collections framework, so we want to be able to choose the right collections. Okay, by the end of the day, you'll be able to differentiate among core collection interfaces, compare lists, set map, queue, DQ, evaluate implementation trade-offs, apply big O reasoning, implement equals and hash code correctly, use iterators safely, and detect performance bottlenecks. Okay, this is not about memorizing classes. It's about engineering judgment. That's what we're concentrating on. Okay, core collection interfaces. So let's talk about those. The collection framework has been around, is built around interfaces. List interface, set, map, queue, DQ. Okay, each defines a behavioral contract. And if you remember, we say contract is the list of rules that we have to abide by. One of the items that we had in the definition. Lists, okay, characteristics, they're ordered, they allow duplicates, and they're index-based, which means that when I'm index-based, I can go and get one particular item immediately. I don't have to go through multiple items to get to the one I want. I can use the index to take that and find out what the given item is. Examples, array lists, linked lists. We use them when order matters and we need positional access. Set characteristics, can't have any duplicates, no guaranteed order. Examples are hash set, link hash set, tree set. Okay. As as with the other classes, and kind of reiterate with this, if you see something and there's an explanation, but that explanation is not sufficient, okay, then take that and run it through chat. Hey, chat, what's the hash set? Chat, what's the link hash set? Okay. I'm looking for you to be able to, for something you don't understand, to research that and find out what the information you need. Because when you get out, when I quote the real world, you heard that term from me probably more than once. I want you to be able to, you may not have all the answers, but I want you to be in a position to know where to get it. Okay. So again, so if there's a term that comes up that you don't quite understand, look it up very easily. Okay. I want to use this when uniqueness matters, excuse me. So here, when we talk about a list, we want to use it when order matters and we need positional access. Set, we're going to use it when uniqueness matters. And I want to make sure I have a unique set. Map, characteristics, it's a key value pairs. Unique keys, so I have a key and a value. Here in the keys, fast lookup. Examples, hash map, link hash map, tree map are basically interfaces that we can use as part of the collection. And when do we use it? We need it when we need fast lookup of an identifier. One of these things I just want to kind of put into effect is that, and you'll see it again, I highlighted it, is that the thing that we're looking at with these kind of techniques or these interfaces is not that we are actually programming it, but we know what we need to pick. Okay. So based on the characteristics of the list I'm trying to put together, that's going to drive me to whether I use a map or whether I use a list or whether I use, uh, yeah, whether I need to put it in a queue, or whether I need to use a set. Based on what I do, what I need is going to drive me to what kind of implementation that I want to use. Okay, so DQ, double-ended queue, can act as a stack, a LIFO, or can act as a FIFO. Okay, so I can basically process from last in, first out sequence, or from first in, first out sequence. Examples, array DQ. The key takeaway here, interfaces define behavior, implementations define performance. Okay, comparing implementations, now we move to behavior. Here, we want to do a little deep dive into Big O, okay, and the processing behind Big O. Big O describes how performance changes as data grows. It does not measure exact speed. This is going to take exactly 30 seconds. But what it does do is it measures growth behavior. So if we have a case of O1, which is constant time, it means that the operation takes the same amount of time no matter how much data you have. If I have 10, it's going to take this X amount of time. If I have 10,000, it's going to take X amount of time. Okay. If I need 10 million, it's going to take X amount of time. Okay, so that's O1. Okay. It does not grow with the input size. Example, accessing an element of an array index. I know I want element 10. Okay, so whether it doesn't matter how many items I have in the list, as long as I have the index, I can get that one item in the same amount of time, regardless of how much data is in the list or in the file. So that's what we're saying here. An example, accessing an element of an array by index, looking at a hash map. Okay. Here's an example. I list I get item 6. We're looking at position 5, but it's item 6. And map.get key. Here's the key. I know this is the exact key of what I want to get. And so I'm accessing that particular item from the map. Okay, implications, scales extremely well. For 10 elements is fast. And for 10 million elements, it's still fast, okay, because of how we're doing that access. Okay, ideal for high performance systems. Design insight, if your system requires frequent lookups at scale, then you want something that is O1. Okay. ON, linear time. What it means is as time grows proportionally with the input size. If I have 10 items, it's going to take me X amount of time. If I have 200 items, it's going to take me more than X amount of time. If I have 10,000, it's going to take me more than that for X amount of time. So in this case, the time grows proportionally with the input size. If the data doubles, the work doubles. Example, searching through a list, checking duplicates manually. Here's basically where we're doing a for, going down through the various, the students objects, the pulling student objects, and then listing the ID from those objects. We're doing one at a time, so the more data, the longer it's going to take. That's ON. Implications, fine for small data sets, become slow at large scale. For large scale, 100 items, it's acceptable. 10 million items, you're probably going to have a serious performance issue because of the 10 million items. Real world meaning, if your application grows, performance degrades steadily. System may feel slower over time. Design insight, ON is accepted when data size is small, okay, and operations is rare. And again, you're thinking about this when you're doing a system and you're saying, well, should I use this particular method in order to access data? And that data is ON. Yeah. Some cases, if I have a small data set, again, there's no problem with that. But we have to analyze and say how I'm actually going to be accessing the data is going to tell me what kind of processing I need to do. What kind of set do I need? O log n is logarithmic time. What it means is as performance grows very slowly, as data increases. Okay, so my performance doesn't go in the same, I guess, performance level as ON, whereas when my number of items increases, then my time's going to increase. Log n cuts that. It says, yeah, as I get bigger, I'm going to grow, but I'm not going to grow as fast as ON. Okay. So that's what it's saying here. Performance grows at very slow as data increases. Often happens with, for example, when we're doing the binary search. I'm sure all of you are familiar with those, or balanced trees. Each step cuts the problem roughly in half. So example, in the binary search, 1,000 items, 10 steps, 1 million items, 20 steps. Yeah, it will go up, but very slowly and nowhere near ON. Okay, yeah, that's powerful. Implications, extremely scalable. Slightly lower than O1, much better than ON. O log n is ideal when you need ordered data and you need a good search performance. Visual comparison, if n is equal to 1 million, I can O1, it's going to take me one step. O log n is probably going to take me roughly 20 steps. And ON is going to take me 1 million steps. Okay. Difference is massive depending on what the effect of O is going to have on your data. Okay, practical design implications. Okay, scalability. O1 and ON scale well. O1 and O log n scale well. ON does not scale well. User experience. Okay, show growth in operations, better responsiveness. System architecture. If your lookup is ON, you can call 1,000. You can call thousands of times. You may accidentally create O log n squared. Okay, which means that not only as my data goes up, the amount of time doesn't go up proportionally, it goes up faster than that. So the time that it's going to take me basically can double or go to the n, O to the n squared power. And that's something I definitely do not want. Excuse me. Trade-off awareness. Sometimes O1 needs more memory. O log n maintains order. And ON is the simplest way to go through things, and acceptable, if it's acceptable, is ON. So big professional question, instead of asking, does it work? Ask, how does it behave when data grows? That is what you should be thinking. I'm doing a system. I want to use one of the Java framework items. How does it behave when my data grows? That's going to determine what I need to use. Okay, so if we look at array list versus linked list, again, one of the items in the Java framework, array list backed by dynamic array, O1 for random access, ON for insertion in the middle. And that's one of the things that you need to look at. If I need to do insertions right in the middle of my list, that's going to be an ON. Okay. So again, based on what I need to do, okay, as far as that data, is going to determine what particular list I'm going to need. Okay, so array list, there's the criteria, linked list, doubly linked list, ON access, O1 insertion. Okay. Ask yourself how often are you be inserting data? In real world, reads are more common than random middle insertions. Therefore, array list is usually superior rather than a linked list. hash versus tree base, hash set, hash map, O1 on average, no ordering guarantee. We won't be guaranteed that we're going to be putting it in a given order because we're using a hash number which may or may not be based on the key. Tree set, tree map, okay. O log n maintains things in sorted order, okay. Not the best in the world, but as my data grows, then my processing grows, but not nearly as much as ON. Okay, if you not need sorted order, hash-based collections are usually faster. Engineering decision, do you need ordering or do you need speed? Do I need to keep things in order or do I need to do it as fast as possible? Those are the kind of decisions you're going to have to come up against to say, well, what am I going to use? What's best? Okay, equals and hash code. Now we talk about we're moving to correctness. Hash-based collections rely on equals and hash code. For example, I have a student with a student ID. If you had two student objects with the same ID into a hash set, would they be considered duplicates? It depends on how you set it up. Okay. In this particular case, what it's saying that I can override it to say that if I do have two with the same ID, then they are in fact the same item and then cause a duplicate. And that will affect depending on which collection items I'm using, whether it's set, map, okay, list, okay. So, but I can do an override to say I'm going to force it to be the same. And that's what's being done here. Same here with the hash code. Okay. I'm defining the item as saying that they are exactly the same if I have the two of them with the same ID. The contact must equal the hash code. Unequal objects may have unequal hash codes. Okay, we talked about what a contract is, how things should process. If we violate the contract, hash map fails. Hash set allows duplicates. Data structure behavior is unpredictable. This is not optional, it's required for correctness. Okay. This is again just saying that sometimes you're going to have to build in correctness. So you're looking at what you're doing. What is the effect of, what do you want to do if you do get a duplicate key or you do get a duplicate ID? That's going to drive, am I okay? Or do I need to force a contract to say, if I do get a duplicate, this is what I need to do. Okay, and that's what's basically being described here. This is just a general summary, big old reasoning. That's what we've gone over these as far as when we might want to use what. Think practically. If you have 1,000,000 elements, O1 versus ON is enormous. Which framework do I use? If I use a framework with ON, okay, and I have 1,000,000 records and it takes me 2 hours, okay, that is because I needed to basically understand what is my performance that I wanted to put into the system when I created it. Okay, again, will the system scale? Theory to reality, if you use linked lists, frequent index lookups, you're creating hidden bottlenecks. If you use tree map unnecessarily, you accept login penalty without benefit. And Big O is not academic. It predicts system behavior. So which one of those O's you fall into will have a definite impact on your system. Okay, here we're just talking about iterators. You talk about looking at stuff and safe transversal. Transversal, just I need to go through every or multiple items to get to the item that I want. That's transversal. Using enhanced loop. Here we're basically taking a string, a lit from a list, and we're outputting and we're printing those out. What if you removed an element? And then what this is kind of addressing is some of the things that you have to consider is that if I'm transversing through a list, but at the same time, I'm making updates to that list, that could cause me a problem. That can give me a concurrent modification exception. Yeah. I'm running through the list. I know there was an item in 4. Okay. when I accessed that item and I went back, say I was going to update it, and that item's gone. Okay, somewhere during the process it got deleted. This can cause concurrent modification exceptions. Okay, so here it says, so why did it happen? Because the structural modification during iteration is unsafe. You normally want to make sure that if you're going through a list or a table, that you're not also, taking that and running it at the same time. That is going to come in when you're doing parallel processing. I create an object, and this object is reading through this list. Okay, I create another object. This object is updating the list. They can run in parallel unless I say that they can't. So those are the kind of considerations that, especially when we're doing an update, that we need to make sure that we're keeping things safe in this situation where I'm transversing through the list, and I'm also giving it the capability to be updated at the same time. Here's just a proposed way of doing that. Here I'm creating the iterator, the string, and I list it. Okay, while IT has next, I get it. Okay, if S equals remove, I remove it. Okay. Well, so what I'm doing here is I'm going through, and as I'm accessing these particular things, I'm designated whether I flagged it as removed or not. Okay, so rather than getting rid of it, okay, what I'm doing here is saying I'm going to tag it as being removed. Okay, this is okay. Yeah, I deleted it. Okay, but I really didn't. But at least I have a marker in there that says there was a record here at one time, but now we removed it. Okay, so the iterators ensure safe removal for lists. Lists, again, you might want to look up list iterator. Allows bidirectional transversal modification during iteration. Okay, with the list iterator. Understand that the list iterator safety prevents runtime failures. Okay, so if you had that situation where I am using, or you are using, needing to go back and forward and be able to handle updating of the list at the same time, a list iterators might be something that you would want to use instead of the regular iterator. Okay, designing scalable systems. Okay, we're moving into architecture, exposure, designing inventory, student inventory. Ask. Here are the kind of questions you need to be asking. Will it grow? Are my lookups frequent? Are my insertions frequent? Is ordering required? Is uniqueness required? Based on that, bad design using array list for membership lookup to a large system. Okay, is not recommended. Okay, using hash set 01. Okay, membership testing. Okay, this is better because I can basically access a record with 01. Poor choice, tree map. Okay, when sorting isn't needed, better choice using hash map for faster access. Scalability is about anticipating growth. Scalability is you asking the questions, how is my data growing? Okay, common collection misuse. Watch for using linked lists without need. Use lists when set is required. Using lists when set is required. Forgetting to override equals and hash code. Okay, to prevent the deletion of items in the list. Okay, while I'm also accessing it. Modify collection during for loop. Sorting unnecessarily, recomputing expensive operations repeatedly. All of these things you should be looking at when you're basically building your system. Refactoring strategy, replace list with set if uniqueness is required. Replace tree map with hash map if order is unnecessary. Extract iteration logic into the helper methods. Measure bottlenecks. Professional developers review collection usage regularly. Yeah. Now, all that's just saying is I might have thought that my number of items in my list was 100, and the search or iterator I use, I could do that fairly quickly. But it was okay today, but I checked it. Yeah, I didn't check it, but I should have checked it next week. Okay, because it doubled, it tripled, it went 10 times. So all this is saying is you need to maybe look at your collection usage on a regular basis to make sure that you haven't basically accidentally went from an O1 to ON situation. Okay. Here, if you cannot justify behavior, performance, scalability, and correctness, then you're guessing. Okay. If you can't do this, you're guessing. And engineering that you'll be putting together, you're an engineer. Engineering is not guessing. Okay, so today we learned about comparing interfaces, evaluating implementations, applying big O reasoning, uh, implement equality correctly, use iterators safely, and design scalable systems. Collections are not just containers. They are architectural decisions. We talk about all the things that we have to determine which one we need to use. When systems fail under load, it's often because of the poor collection source. We picked the wrong one. Okay. Your job is to prevent that. Okay. With that, I'll see you next week. Not next week. We will see you next week, but I'm hoping that you guys will look at this first, and that for those in class, we'll have a little deeper dive into these items and give you a chance to ask some questions when we do the in-class lecture. For those who are online, the in-class lecture will also be available to you for your reading enjoyment. Okay, so everyone, thank you, and we'll see you later. Bye.